Okay, so bar bodies. Discovered by Dr. Murray Barr, hence the name. What he found was when one of the X chromosomes in females randomly becomes inactive, it shows up as a small dark spot of chromatin in the nucleus of the female. And we call that a bar body. So the X chromosome simply just crumples up, okay, and yeah, becomes inactive. And this will usually happen in just regular somatic cells or body cells. And when that happens, only the traits that are on the remaining chromosome will be expressed in those cells. Okay. So when they're regular body cells, because we have so many cells, it's usually not that noticeable that there's anything wrong. But some cells will express a certain trait and some others won't. And there actually is a condition which happens in females, is a skin disorder called, and I don't even know how to say it, anhydrotic ectodermal dysplasia, where she will have patches of skin that will contain sweat glands and patches that do not. Okay, and that's because of these bar bodies, these inactive chromosomes. Okay, and this mosaic, so this patchy skin is a expression of some X chromosomes being activated and some not. And of course, if this happens in a sex chromosome, you would end up with a person with Turner syndrome. Okay, so lesson 19.2. It continues on page 7 of your notes. Okay, really all I want to teach you in this lesson is how to do chromosome mapping. All the other information that I'll be presenting up until I teach you how to chromosome map is how scientists like Thomas Morgan were able to map the chromosomes. Okay, and so there's a lot of backstory, and I apologize for that. Chromosome mapping itself is very easy. The backstory leading up to it can get a little bit confusing, so I don't want you to stumble over that. I don't want you to worry about that so much. Because once we get to the mapping, you're going to find that part is quite easy. So let's get to the backstory. So we are talking about our linked genes. Remember, they are located on the same chromosome, and they do not segregate independently during meiosis. Okay, so if you have chromosomes gene A and gene B on the same chromosome, they will always travel together. Okay? When this happens, you get a typical phenotypic ratio. These do not occur. You still get some variation because of crossing over during prophase 1. Okay, and then I found this graphic. Okay, so here we have some linked genes. Genes A and B are on the same chromosome. So you're going to get one from, one is maternal, one is paternal. Okay, so they're going to cross over during prophase 1, and you can see that you can get, different combinations of alleles in your gametes. So instead of having, both of them being big A, big A, big A, one of them is big A, big A, big B. One of the chromosomes will have a big A and a small b instead. And same with the, the paternal chromosomes. Instead of both being small a, small b, you could have one that has small a, big B because of crossing over. So you still have the same genes on the same chromosome, but the alleles could change. So to review, the non-linked genes, they can separate independently or segregate independently. Okay, so I mean it looks like chromosome Y, but there's the gene Y and the gene R on separate chromosomes they'll segregate independently. Linked genes, however, they're going to travel together and end up in the same gamete together. Okay, and so through this crossing over, the gene combinations of a single chromosome can be altered as it's passed from generation to generation. So just meaning you're going to have the same gene in your offspring, but not necessarily the same allele combinations because of crossing over. Now listen, about this crossing over, it happens more frequently between genes located far apart on the chromosome than those that are really close together. And the reason why is that genes stay together on the same chromosome after prophase 1 have very low crossover frequencies. Okay, so just another graphic to show what happens with crossing over. You can see that gene C is going to cross over more frequently because it's, it's on the end. It's just a more convenient place to cross over. Okay, so how did geneticists learn to figure out where the genes are on the chromosomes? And it all has to do with crossing over. And we call these recombinations. And so the more frequent you get a recombination, you're going to assume that the genes are farther apart, the more frequently they recombine. So let's talk about this again. So a linkage group is a group of linked genes on a chromosome. So they're the ones that are on the same chromosome. Crossing over during prophase 1 results in the exact exchange of alleles. Well, that same fruit fly guy, Thomas Morgan, he was able to determine that the frequency of crossovers between any two genes in a linkage group was always the same. So the frequency of crossing over between any two genes can be stated as a percentage. Okay, and it's these crossover percentages that helped him map the chromosomes. You get them by dividing the number of recombinations, okay, so the number of time that it crosses over the total number of offspring. So the percentage of crossovers is related to the actual physical distance, meaning the farther away they are from each other, the genes are far from each other, they're going to cross over more often than genes that are close together. Okay, so the genes that are far apart, they're going to cross over more frequently, more often than those that are close together. So E and G are going to have a higher crossover frequency than genes E and F. Okay, and so I'll use the fruit fly example again to show you kind of how he did this. So he crossed two heterozygous individuals who showed linkage in the two characteristics he was looking at. So big A is like the color of them. So wild color and black, and then how their wings looked, so whether they were straight wings or curved wings. Okay, so he took two individuals, one homozygous dominant, one wild color with straight wings, and one black with curved wings. Since the genes are linked on the same chromosome, there were fewer possible gametes. Okay, so your gametes look like this. Okay, the dominant genes travel together, the recessive genes travel together. And so because of this, we've got some very predictable phenotypes. We all have 3 out of the 4 are of like wild type, and what is that? Straight wings. And only 1 is gonna be the black with curved wings. Okay, so it's always a 3-to-1 ratio. But what Morgan observed was 4. He attributed the other 2 phenotypes as crossing over. Okay, so what he ended up with, these are our predictable ones, which would normally be a 3-to-1 ratio. Okay, so we would normally have 75% showing the dominant phenotypes, and normally we would have 25% showing the recessive phenotypes. But then there were these oddball combinations. Okay, you'd have, you know, nine of all 400 of them showing the, you know, dominant for one trait and recessive for the next, and 9 of them showing dominant instead for body color and recessive for wing shape. So these were the unexpected phenotypes. And he concluded that these were the result of crossing over. Okay, so these are the result of crossing over. Okay, and then to calculate crossover percentages, okay, he took the number of crossovers, which is 18, divided by the total number of fruit flies, which is 400. Okay, and he expressed that as a percent. Okay, so the crossover frequencies between gene A and gene B is 4.5%. Okay, so this is how he got crossover percentages. All you need to know is what to do with these crossover percentages. The percentage of crossovers is related to the actual physical distance between the 2 genes on the chromosome, meaning genes that are further away from one another have higher percentages, and genes that are close to each other will have lower percentages. If you know what the crossover percentages are, you can easily map the gene. Okay, so the crossover frequencies between gene B and VG, they have a crossover frequency of 17%. Between B and CN has a crossover frequency of 8%. And between CN and VG has a crossover frequency of 9%. And so you can kind of see the one that has the largest crossover frequency, those would go on the ends. So these have the largest crossover frequency, so we put these on the ends of the chromosome. Okay, and then if you notice, these other 2 frequencies, they add up to 17%. Okay, so that means the middle gene, the CN, would be somewhere in between those. Okay, and then when genes are in the correct order on a chromosome, the map distances between the different genes can be added together. So let's try some examples of this. Oh, not there. All right. Okay, and you'll find this one. This is on page 9. Okay, so it gives you 3 choices. A geneticist finds that crossover frequencies between gene A and B is 12%. Between gene B and C is 7%. And between A and C is 5%. What is the order and relative distance of these 3 genes on the chromosome? It gives you 3 choices on your page, but if we were to just draw our own, you'd start with the chromosome. Okay, you look for the crossover frequencies that are the highest, and the highest is 12. So the highest one, you would put these genes on the ends. A and B are at the end. Okay, and we know that these are 12, I call them 12 units, 12 crossover units apart. And you'll notice B and C, if you add these together, they equal 12. So we have A and B on either end. We just need to place C. So C, A and C is only 5 units. B and C is 7 units. Okay, so we wouldn't put C right in the middle. C would be a little bit closer to A. Okay, so because between A and C is 5 units, and between C and B should be 7 crossover units. All right, and okay, so if we look at our answers on our page, you'll see that you know, the last example is right. Okay, here's another example. Geneticists find the crossover frequency between A and B is 4%. The crossover frequency between B and C is 14%. And between A and C is 10%. Okay, you draw your chromosome. Okay, you find the one with the largest frequency, and that's B and C. So you're going to put these on the ends. Okay, so they're like 14 units apart. Okay, that would mean that A is in the middle somewhere. Okay, so A and B are like 4 units apart. No, actually, I need to draw that there. And A and C are 10 units apart. And that's kind of how you do it. How are we doing with chromosome mapping? Okay, let's do this one together. So B. I don't think I have this one. Oh no, you don't have this example. Oh, I don't have any more examples. Okay. Try the ones that are, oh wait, here we go. Oh, you don't have any of these either, do you? All right. Just try the other two examples. Oh, there's more. Yeah, the other two examples on pages 10 and 11. So you got questions 3, 4, and then on page 11, 1, 2, and 3. Just try answering those, and I'll kind of meet back with you in about 5 minutes, and we'll just go over those answers.